I'm R. Prabha, Assistant Professor in the Department of ECE, SNS College of Technology. In this video, we will discuss the topic on retarded potentials for the course antennas and wave propagation. So now the contents of today's video. First, we are recalling the previous topic: antenna parameters, antenna impedance, polarization, beam width, bandwidth, antenna temperature, and also Friis transmission formula. After that, we'll see retarded potentials. We discuss the retarded electric and magnetic potential. Finally, we'll see the applications and also the summary part is the mind map. So, the recap of previous topic, essential antenna parameters. We have seen antenna impedance. It is the complex term which consists of resistance and reactance, which determines the power transfer efficiency at the feed point of the antenna. And next is the polarization. Polarization is nothing but orientation of electric field, and there are a variety of types like linear, elliptical, and also circular polarization. Next is the beam width and bandwidth. Beam width is the angular width of the major lobe. Bandwidth is nothing but the useful radiation frequency range. And next is the antenna temperature. We have seen the noise temperature and the power transfer relation in the Friis transmission formula between transmitting and receiving antennas. So now in the empathy part, the challenge is why to study this retarded potential. So there is a physical reality, that is the electromagnetic disturbances don't propagate instantaneously because the information always travels at some speed, which is the speed of light. So here the engineering problem is when designing antenna, we must also account for the time delay between source oscillation and also the field observation at distant point. Now the key question is how to calculate the fields when the cause and effect are separated in time. So now coming to the defining part, we are defining the retarded potentials. So first we see the retardation time. So retardation means delay. So the delay here is taken as T minus R by C, the time delay for the disturbance to propagate from source to the field of observation. So here T is the time and R represents the distance between the source to the distant point or the field of observation, and c is the velocity of light, 3 into 10 power 8 meters per second. And next we are seeing there are two types of potentials. One is scalar potential and another one is vector potential. Scalar potential is nothing but scalar electric potential. This is scalar because for electric field the source is the charge. Since charge is the scalar quantity, we call this electric potential as scalar electric potential. So and it depends on the charge distribution at earlier time delayed by distance divided by the speed of light. And next is magnetic vector potential. We are calling this magnetic potential as vector because the magnetic field source is the current. So current consists of current is a vector quantity, so we call this magnetic potential as magnetic vector potential. It also depends on current density at retarded time instance. So now in the ideate part, we are going to see the physical interpretation through analogy. The source disturbance is the charge acceleration, which creates electromagnetic disturbance in local space-time. So next is the propagation delay. When the information travels outward at light speed, which creates causality gap between source and field. So we call it as the propagation delay. And next is delayed observation. So here the observer measures the field corresponding to earlier source configuration, not present state. So we can observe this with the water wave analogy, observing ripples reaching shore, effects arrives after cause. So the derivation of this potential is, first we see the scalar electric potential from the Maxwell's equation. del squared V minus mu naught epsilon naught. Dou squared V by dou T squared is nothing but minus rho by epsilon naught. And the magnetic case, del squared A minus mu naught epsilon naught dou squared A by dou T squared is equal to minus rho naught J. So here V is the scalar electric potential, A is magnetic vector potential, and epsilon naught mu naught are permittivities and permeabilities of free space. Rho is the charge density, J is the current density. So now we can relate the expression for retarded scalar potential is V of r comma t is equal to 1 by 4 pi epsilon naught integration of rho of r dash minus comma t minus r by c by r dv dash. Here the t minus r by c, we call it as retardation time, and capital R is that distance between the point of observation to the source, and it is nothing but r minus r dash, the magnitude value. And next is the expression for retarded magnetic vector potential, and this is given by A of r comma t is equal to mu naught by 4 pi integral of j comma r dash comma t minus r by c by capital R into dv dash. So here this term j r dash comma t minus r by c is nothing but current density at a retarded time. So now we are going to see the prototype part. So we are application to antenna radiation. So there are 4 steps in this. In the first step we are going to see the source current. So source current here is the time varying current in the antenna element which produces accelerating charges. Next, from the source current we derive the electric and magnetic fields. So in the next step we calculate the potentials, and the radiation, we analyze the far field radiation. And coming to the real world applications, the retarded potentials impact in electromagnetic understanding like astrophysics, telecommunications, and numerical simulations. So finally, mind map, the summary part. So far we have seen antenna fundamentals and a recap of antenna parameters. We studied 2 types of potentials, retarded scalar and retarded vector potential. We have seen the retardation concept, and finally we have seen the various field of applications of this retarded potentials. Thank you.